into the remote sensing technology, what it is, how it collects the information, and where all it can be utilized specifically in your applications where you're dealing with plants. So I'll be focusing on vegetation aspect, how this technology can be utilized and what are the different ranges of data sets which is being acquired using the satellite platforms. Now remote sensing, as you can see from here, is nothing but the art and science of acquiring information about the Earth's surface. So in fact all of you are also doing remote sensing at the moment. You're reading this without actually touching it. So, or in a more scientific way, if we say science of making measurements or the geometric and thematic properties. Geometric relates to the shape, size, orientation, air, I mean all these aspects are considered, and thematic is related to what it is on the ground, whether it is a forest, agriculture, what attribute it is there on the Earth's surface without being actually physical contact with the Earth's surface features. So it enables us to observe and study nature in ways that otherwise is beyond human capabilities. We are restricted to visualization in only certain part of the electromagnetic spectrum. So it enables us to observe things which is difficult or it is beyond human capabilities across greater distances and at wavelengths which are invisible to human eyes. We can't even venture, there are inaccessible areas. So remote sensing provides us with platforms, with the facility to cover or acquire information in those areas. Now this is another new definition which has come up, which says it is basically for the management, improving natural resource management. This is the entire remote sensing process where you see that the data which is there from the ground gets reflected. This is the Earth's surface. The energy which is there on the Earth, I mean coming from the natural source as a sun, falls on the object, what light we are seeing gets reflected, is measured by the satellite and is converted into, the energy which is reflected is converted into a number. And the size of this cell which you see is related to the resolution. What is the smallest area you are able to see on the ground? And it can vary from few centimeters to kilometers, depending on satellite mission, objectives, purposes. And then it can be displayed into an image or a picture, and that data can be analyzed for various ranges of applications. Now this is what is there. What is recorded is basically the energy patterns. What is measured by satellite is nothing but the energy patterns, how the land cover behaves with respect to or interacts with respect to these energy in the visible region, in the infrared and the other areas like the microwaves. So what is measured is nothing but the interaction of the electromagnetic radiation with the object. That is what we call as signatures or energy patterns, you can say. So remote sensing has a flexibility, range of measurement, invisible areas, synoptic coverage, variable resolution it provides you. The size of the grid which I said is different, it's dynamic in nature. It can provide you time series. I mean you can have every half an hour data to a data set across few years, decades, you have this information, and it can cater to a multitude of applications. Specifically in your case, if I say for vegetation identification, monitoring, prediction of these plants at local, regional and global levels. So remote sensing data is objective and quantitative in nature, observation in inaccessible areas and easy integration with other sources like you had in a geographic information system for better decision making, planning and conservation purposes it can be utilized. Now if we talk about, when we said we have this complete range of electromagnetic spectrum, this can be divided into different regions, what we call as optical, thermal, radar and lidar. These are using data from, utilizing different ranges of the electromagnetic spectrum. That's why the name comes, and each of these data sets is characterized by different resolutions. So what is there, if I talk about the optical remote sensing, this caters to the visible and the reflective infrared remote sensing, which is in the visible part and to some extent the infrared portion of the electromagnetic radiations. So from here what we measure is the amount of energy which is reflected by the object. From the sun it receives the energy, it reflects, it's measured. Then the next part is the thermal radiation, in which any object, when there is sun rays in the morning, gets heated up, land gets heated up. That heat energy gets dissipated, it gets emitted. So the region of the wavelength that corresponds to around from 3 micrometers to 35 micrometers is the infrared. Anyway, infrared is associated to heat, those infrared heaters are there. So that is measuring the temperature of the object. So it's related to the temperature of the object, that is called as thermal remote sensing. Then in the microwave remote sensing, we use the microwave radiations for measuring the energy being reflected. Now microwaves are active sensors where the energy falls on the object and gets, it creates its own energy and it reflects back. So that is, its signal incoming direction and outgoing direction are same. So that's it is called as backscattered. In case of sun, if you look at this, there are two directions, incoming, outgoing. In microwave, incoming, outgoing and the same. That's why that is also a reflected component, but in the microwave portion, but since it is being scattered back in the same direction from where the energy is coming, it is known as the backscattered radiation. And these are the wavelength regions which is being utilized for optical, thermal and microwave remote sensing. Each of them give you different kind of data sets. Now if we talk about the optical remote sensing first, how the feature behaves or what is recorded in case of optical remote sensing, it is basically the energy pattern, how the object behaves with respect to the different energy levels. That is from 0.4 at different, this is blue. If you look at the previous spectra, what we saw, it is 0.4 is violet to blue, 0.5 is green wavelength, red and so on. So how an object interacts with different ranges of wavelength, that is what is measured in the optical remote sensing. So this is a general profile, if you look, of different land cover features like vegetation, dry soil, wet soil, clear water, turbid. Now the energy pattern or the interaction mechanism of each and every land cover is totally different. And this difference is what is recorded. And if I am able to categorize, using this differentiation, I am able to categorize them into different classes or objects on the Earth's surface. So if you look for another example which I can show is for a vegetation, how it is working. Now if any object is green in color, it will reflect more in green and the blue and the red colors gets absorbed. So this is getting absorbed and this is reflecting high. If the leaf was red in color, red would be reflected high, blue and green would be absorbed. So the value which is you are measuring in one band will be high, in the other wavelength it will be less. And using this all together in combination, I can infer what is this feature on ground. Now in case of vegetation, what the problem here is, it is green which is reflecting. So there is a difference between an object is green and a leaf is green. Both will reflect in high in green. So how can I differentiate it's a leaf or an other object? So in that case, I use the other wavelength. Now infrared is one aspect where the cell structure inside the leaf, they play a crucial role in the infrared. And because of that, it reflects very high energy in the infrared and the other green object will not do so. So in this wavelength, they may be same, but in the other, they are different. So I am using the other wavelength data to distinguish between two similarly objects in one band or one wavelength. So that's how I cannot do remote sensing with only one band. With good accuracy. For that I need a range of wavelength where their characteristics are varying. So in one of them they may be similar, but across the wavelength somewhere down the line you will find there will be differences. Now this is crucial regions for vegetation. Because of the water in the leaf water content, there is an absorption. They absorb the radiations. Now if it is a stressed leaf, they will not be there. This reflection pattern would be straight in nature. So if I have data of those wavelengths, I can study whether it's a stressed plant or a healthy plant. So that may not be very clear from this data, but if I have data sets across this wavelength, I can differentiate. So that is the beauty of the multispectral remote sensing. You are not using one band or one wavelength, but a range of wavelengths and capturing the variations in them. See, this is that example which I was telling you, that if you have variation in the leaf color, then that same is reflected in the energy pattern variations. And using this, I can characterize the feature easily. Right? This is another example which I was mentioning between the stressed, healthy vegetation. The differentiation can be seen. Though here if you see large, but it is exaggerated, but the value may be very small difference. But here it is significantly higher.
Desert plants must be show high absorption. Desert plants, because they are having the
In that region, in the shortwave infrared, yes. But in the infrared, the cell structure, water doesn't play a role in the infrared, it's in the other part. And similarly for agriculture crops which have a phenological cycle, I can capture even the phenology. If I have temporal variations, I can capture the phenology. This is again a difference, another curve which is highlighting different types of land cover features, which says concrete, sandy loam, again. So here in this region if you see, many objects, they are appearing very similar, overlapping. But the moment you go in the other area, infrared area, you will find vast separation.
And there are green organisms or other like grasshoppers and all.
Grasshoppers is very small, no?
Small.
So that remote sensing is difficult to measure. You should have a pixel resolution so much that you can see a grasshopper on the image. It's for the general, larger. Otherwise, we can't see even humans also from the satellite because the resolution is not that you can identify. For that, aircrafts and all where you have to fly down, and still even to get a grasshopper, that level of detail is generally from the very low observations or maybe ground level. From satellite, which is at an altitude of very high, around 1,000 kilometers, it's very difficult to identify a small grasshopper. So it's for gregarious patches, large patches where you can identify.
group of grasshoppers we can identify. The groups of
Group mean how much? It should be a larger approximate, yeah, having an area extent of a minimum of 1 meter, that also with very high resolution satellites, 1 meter square or something of that order.
Is it any minimum dimension?
Yeah, which is, no, minimum is not there. Now with the advancement in technology, we are moving towards centimeter, which I said. Targeted is 25 centimeter, currently we have 40 centimeters, but still there are limitations. So another example graphically, if you see, this is with only one black and white photography which we had earlier. It was very difficult to distinguish between a deciduous and a conifer, but when we went into the infrared, this variation became very distinct. And we can say where is that conifer patch and where is the deciduous. So in one wavelength they appear very similar, in the other. So this is how remote sensing works. This is another example of water feature. Not very clear, in the infrared becomes clear. This is an example of snow and cloud. Both are appearing white. But the moment you go to the shortwave infrared where water absorption is there, because of that, snow has water content, absorbs the radiation. Cloud, it cannot penetrate, the radiations cannot penetrate the cloud cover, reach the earth's surface. They reflect it from the top itself, it is white. So optical remote sensing cannot penetrate the cloud cover. Okay. So this is another example of multispectral. See, I can create a color image of, you have a normal camera RGB, 3 colors. Using those 3 colors, I have ranges of wavelength. I can recreate back colors. Now if you look at this image, there is a burnt patch here. In this region, there is a burnt patch, right, which is not visible here. Now, in one combination, this is another band combination we have taken, near infrared. Now see, another band where this becomes evident. So in the previous one, it is not visible at all here, very clearly distinct. Then the near infrared, another band of infrared very close to it, and here it becomes clear. So this is how you can easily demarcate the feature, separate it out from the others. So this is what we call it as different kinds of remote sensing. We have broadband, where we are recording in broader regions of wavelength. So that, what it does is, it doesn't allow us to give the strength to differentiate on many features using that data sets. Then it goes to multispectral. Within this broadband region, I have many smaller measurements. This again, I can have still small observations. So when I am reducing it, my strength of discrimination, power of discrimination becomes stronger, and identification becomes stronger. Like what we saw with the black and white photograph, I couldn't differentiate the 2 forest type. The moment I started recording with smaller energy levels, that power improved and we were able to discriminate. Another application which we said, this is with respect to the hyperspectral, where we are having very fine levels of wavelength band or spectral information where we are measuring. That is known as hyperspectral, and it has a large range of application. This is has a strength of, in the previous case, we could differentiate the major types. With hyperspectral, I can identify the type, what is that plant, what is that medicinal plant. If it is in a larger area, I can say this is this plant on ground. The species level differentiation can be done with hyperspectral. That is the advantage of the hyperspectral. So there I am able to discriminate between the 2 objects. Here I am able to identify the species also on the satellite images. So this is an example what we did with the hyperspectral data, where different species of the forest types which are available in the area could be identified using this hyperspectral data, which was not possible with a multispectral data. In multispectral, I had a broader categories, deciduous, conifer. But what is the species level, like lantana, eucalyptus, then your pinus, sal, that is shorter, each and every species, if it is discernible on the satellite data sets. The area, resolution, again restricted to the resolution of the satellite image.
Suppose there is a branch, this is oak forest is there, or pine forest is there, and there are some shrubs
Beneath it.
Beneath it.
That using optical data, it is difficult. But there is another data, microwave data, which has a capability to penetrate.
Yes, because that is also required some time to us. So, yes.
In this, if it is a dense canopy, it cannot give you subsurface information. This optical remote sensing gives you only the surface. It cannot penetrate the canopy to give you subsurface.
So
microwave
undergrowth will be not covered in that.
In this undergrowth will not be covered. Then LIDAR and microwave, which we will see, some of the wavelengths of microwave will give you the. So the factors which influence the amount of energy, which is the energy pattern which we saw, these are some of the factors which is there, which influence or causes the variation in energy patterns in the different object. Now this is the related to thermal remote sensing we said, which is measuring heat. Now this is a condition which is with your optical data, this is the thermal data. Now from this you can see that in the optical there is a forest fire. Now this forest fire, in this case what you are seeing in the optical is only the smoke plumes. You do not know the mouth of the fire. Thermal data sets, that thermal wavelength, infrared wavelength, can penetrate the smoke plumes and exactly show the mouth of the fire. So thermal remote sensing plays a role where specifically in related to forest fires, volcanic activity, or even land surface temperatures. Even the vegetation has different temperatures. That also can be measured with these thermal bands.
Please repeat this. Volcanoes.
Forest fires, coal fires, underground the coal fires. Many applications are there, some of them which I mentioned. Urban heat, urban temperatures, urban heat islands for urban surfaces. This is the same example with different bands and how in case of this band you are able to identify the mouth of the fire. This is with very high resolution of thermal remote sensing where you are doing it from the airborne platform. You can get streets which are warmer. Everything, temperature variations easily you can identify. It's related to the temperature of the object which is mapped using thermal data sets. Then this is what I was mentioning is the microwave remote sensing. The main advantage of microwave remote sensing is this is active remote sensing. It is providing its own source of energy levels. And another example is it can penetrate the cloud cover in even any weather conditions. It gives you the data. So it is all weather, all time. Even since it is providing its own source of energy, it can operate during night time. So all day, all weather. And another advantage is what you were mentioning, it penetrates the canopy. So these are some of the applications, broader applications where radar can be used for vegetation mapping, monitoring, in terms of mapping the forest land cover, mapping wetlands, its structural attributes using some of the radar data sets, interferometry, height, basal area, biomass, volume, monitoring the disturbances, the changes and the photosynthetic processes. So these are some of the parameters which govern the reflection or the reflection of the energy with respect to the different terrain features or system parameters. Now if I talk about the scattering mechanism, energy is coming and is scattered back. So scattering can be from the flat surface. In case of vegetation, it takes a case volume scattering because from branches also it gets reflected. So it's a multiple reflection. So that's what is called as volume scattering. So from the signal itself we can categorize which is surface, which is volume, and volume if it is there generally it is from the vegetation, and that is enabling us to characterize different features. There it was the total reflection at different wavelength, here it is the type of scattering mechanism. Okay. And here you can see how the different wavelengths are penetrating. X band, that is at 3 centimeter level, it is able to give you to some level of vegetation canopy. As you move towards the L band, it can go to the ground level and give you information of the shrubs and all. This is the example of how same image, same area acquired on same day. In optical there are clouds, in microwave it can penetrate the cloud and give you a clear picture. So in seasons where you have monsoon seasons and all, microwave gives you information. Another is very useful for vegetation application is LiDAR, which is light detection and ranging. It's also an active system like radars, but it's not an imaging system. It doesn't give you picture. It works on the principle that the energy which is sent from the satellite comes, falls on the object, gets reflected back. Now what we are measuring is the time of signal sent and the time of signal received. I mean when it is reaching the satellite. With this and you knowing the speed of light, I can calculate where this position is. Now the same signal, same time signal is sent here and is sent on the ground. Now time difference would be different. Measuring this time difference, I can know the height of the object. So, and it also enables me to give me the structure. There will be many reflections from here. It will help me to build the structure of the plant or the vegetation stand. So this also helps you in vegetation studies to calculate the area, the structure and the height of the vegetation or any object. If it is an urban area, it will be with the buildings heights. Right? Now if you talk about remote sensing platforms, there are different remote sensing platforms: space-based, air-based, ocean-based and land-based. They can be anywhere, space, air, from wherever. I am not touching it, but from distance I am making measurements. Even on ground, if I take a photograph, that also is a remote sensing application. But these are for different applications. Airspace, which gives you, another one has been added now, is the unmanned aerial vehicles or drones, which you are calling about, UAVs, which comes in between air-based and land-based. Somewhere between the air-based and the land-based, they are at very low altitude, around 500 meters from the earth's surface, and gives you with a fairly high resolution the observations from the land features. Land-based are generally for calibration of, validation of my satellite measurements, or air, from satellite, air-based, and similarly oceans are also for validation or calibration from air and or space-based data sets. So this is what I was telling. Drone is another platform which is coming between air and land. The advantage is you can have a flight below the cloud cover. So optical data, even there is a cloud cover, you can operate the drones below and collect the data. So it will not be affected, and it provides you higher resolution. These are the two major platforms, or you can say, of satellite remote sensing. One is geostationary, other is the polar orbits. Geostationary are the ones which are at a very high altitude of 36,000 kilometers, and it provides data sets for meteorological and weather communication, weather and communication applications. Because the speed of the satellite and the speed of rotation of the earth around its own axis is same. It continuously monitors the same area and provides you this data. I will just show you how the sun synchronous or the polar orbit operates. How it works, it takes the acquisition, the earth is rotating, and subsequently another part of the area is covered. And this is how in the complete rotation of the earth, different areas or different parts of the earth's surface gets recorded. And these gaps which you see, they are subsequently filled in. Yeah. Different geostationary satellites which India has launched for communication and weather applications. They are used for basically, as I said, for communication, weather, and developmental plans like telehealth, EduSat, which was utilized. Now initially when I said all data sets, whether it is microwave, thermal or optical, they are characterized by these 4 parameters. So depending on your application, you need to choose the data. So each satellite mission differs in these 4 terms. Now spatial resolution, as we saw initially, was the size of the area which is seen, smallest area seen on the ground. So in this case, one block of is 56 by 56 meters on the ground. And as we move away, this is 56, 30, 23, 15, 5.8, 4 meters and 1 meter. Now if you look at it, the level of detail you can discern is different. Here you get a broad impression, and here the finest detail to the road, and if I zoom it up, I can see even the vehicles on the road. So these are some of the satellites with variable spatial resolution. We categorize them as coarse, medium, high, very high resolutions. So coarse resolutions, they are of the order of 1 kilometer. So some global satellites are there which give you 1 kilometer data sets, and these data sets are free to download on the web. So they give you daily data of 1 kilometer of their region, easily available. So different products are also available, and the raw data sets. Then moderate to medium resolution, their category is from, if I say 30 meters, 50 meters, 60 meters, 100 meters. So there are large range of satellites which provide you these data sets. Now in this case, my acquisition mechanism is every day. I have a very coarse, but I have everyday repetitivity. In this case, it is a medium resolution. It is better, but my repetitivity ranges from 5 days to 10 days to 15 days. So accordingly, different satellites have been designed. So in case of IRIS, there is a sensor called wide field sensor, which gives you around 56 to 60 meters optimum resolution, and the repetitivity is 5 days. So for vegetation studies, every 5 days, for phenological studies, for understanding the phenology, this data is useful. Then we have the high resolution, which is around, you can say 5 to 10 meters of resolution, of the order from 1 to 5 meters in that region. You have ResourceSat, Iconos, QuickBird, WorldView, which is having a variable resolution from between 1 to 5 meters and can be used for different applications. Very high resolution is generally now a new term came after the launch of very high resolution satellites, which give you the spatial resolution of less than a meter. So these are some of the satellites. India's Cartosat 2-3, which is 80 centimeters, and across the world it's 40 centimeters. So you can see the difference in the object itself. The feature itself has, as the resolution changes. This is an oak forest, Allanus forest, oak mixed and oak pine, how they appear on the satellite data sets. The textures is varying. Now here, these are different types of forest, right? The same using high resolution. Now a comparison between, this is around 1 meter data sets and this is 5 meters. How the appearance changes with the resolution. And using very high resolution data sets, I can extract the tree areas. I can extract individual trees which are joined together, or a clump or group of trees. Using automated measures, using image processing approaches, this can be extracted from very high resolution satellite data sets. Then next is the spectral resolution, which we just mentioned, that how many wavelengths I am able to record in. So the larger number of bands I have, wavelength information I have, better discerning capabilities I will have. And this with the help of spectral resolution, that means more number of information I have, wavelength information I have, I'll be better able to differentiate between different type of species of vegetation or any land cover on the ground, whether it's a mineral, vegetation species, urban material. So more information here I have, the differentiation improves. I can easily identify with hyperspectral, I can identify the species. So these are general applications for the different wavelengths. The visible is used for vegetation mapping. I have organized in terms of the plant species, but it can be used for various other geological urban studies also. The thermal infrared is for active fire, burn scar, hotspots. Microwave, again for vegetation structures, all these applications. Then is the radiometric resolution, which is related to the number of gray levels which is measured. The energy which is reflected is recorded in form of numbers. What is the number of levels it is recorded in? That is related to radiometric. If I record it in 2 levels, 0 and 1, the image would look like a chessboard, black and white. The more shades of grey I give, better differentiation between features are there. So this is one example. This is a 2-bit data and this is a 8-bit data. You can see the same area, you can see better clarity with higher number of grey levels. Then temporal is basically the time after which satellite repeats itself and collects the information of the same area, picture of the same area. Now initially most of the satellites, they had a fixed geometry, fixed platform, only sensors could be tilted. So because of that, once in a while it could, if it was tilted, you can have a repetitivity with a different angle. But nowadays most of the satellites are becoming with a platform which is agile in nature. That means they can be rotated, not the sensor, but the whole satellite can be rotated. So in case of emergencies, disasters, if that satellite has that agility, they are tilted and information is acquired as and when needed if it is in close vicinity to the area. So for different applications, the requirement of temporal resolution is also different. But in general, if you have coarser resolution, high temporal resolution, very high resolution data, the temporal resolution is less. Because coarser spatial resolution, it covers a wide swath of land surface and it comes back very frequently. With very high resolution data, the swath is less. It's just maybe 11 kilometers, 10 kilometers. So it takes longer time to fill these gaps and come back again. So but there is always a trade-off between the resolution and the temporal resolution. So what do you want? High temporal, low swath for global level information, medium temporal resolution, fairly medium resolution satellites with 250, 100 meters resolution for regional level information, then medium spatial for local level, and then high for a local location specific information. So what kind of studies you are offering, regional, global or city level or local level, accordingly you will choose the data sets. Now these are characteristics of some of the Indian satellites which we have. IRIS, Indian Remote Sensing Satellite 1A and 1B. These were the first generation of remote sensing satellites which was launched by India. Then came IRIS 1C and 1D, which followed with stereo capability also, meaning this camera can be tilted to get a stereo acquisition which gives you information about the terrain height also. So it had multispectral as well as panchromatic camera for terrain information. Then the third generation is the ResourceSat series, which is a very unique satellite of the country, which is having a multi-tier information. From the same satellite, there are 3 cameras giving you 3 different spatial resolution. So same area is acquired with 3 resolutions. And the cameras are 56 meters, 23.5 and 5.3. So regional to a local level, location specific studies. Okay. Then Cartosat, which is the satellite for topographical information. The name itself is Cartographic Application Satellite, which provides you stereo coverages for generating the digital elevation model or the terrain information about the height variations onto the terrain. The complete elevation model for the country has been generated and uploaded onto the Bhuvan website. So anybody can download for any specific area and operate on it, work with it. So it has 2 cameras which are looking backward and forward. The combination of these 2 together works and you get a stereo and from which you get a height. For the same is the principle which we have 2 eyes. From 2 eyes, if you observe any object with 1 eye, it appears here. If you close with the other, there is a shift in its position. That shift is related to the height of the object or the depth of the object. Same principle is adopted here to generate the height information. Same object or same area is viewed from 2 angles. Then Cartosat 2, which has a single camera with 80 centimeter of spatial resolution. So it has only one wavelength data. Cartosat 1 and Cartosat 2, they are not multispectral, they are single band. And these are some of the worldwide sensors which are used across the globe. Those were Indian satellites. These are across the globe where are high resolution to medium resolution satellites. Iconos, QuickBird, WorldView, RapidEye. RapidEye is one more sensor which has high temporal resolution as well as high spatial resolution. It's of the order of 6 meters. And what they have done, they have a constellation of 5 satellites which are just identical to each other. And they are running parallel to, continuously one after the other like a train. So this takes the data, after second or second day the other satellite comes, then the next, then the next. So temporal repetitivity is improved by having a similar constellation of 5 satellites. They are programmed just running one after the other. These are some of the microwave sensors which are available. NVSat from the Europe, then RadarSat from Canadian Space Agency. RESAT is the India satellite which works on C-band with 3 to 50 meter spatial resolution and the revisit of 25 days. And these are some of the private sectors which we just saw. The highest we said 40 centimeters. And recently some of the observations are Earth's observations. Sentinel satellites have been launched. These data sets, they are from the optical as well as the microwave region. And most of the data sets are also free for usage. And this ISAT, which was launched by US, was the first LIDAR sensor. Otherwise, LIDAR is generally airborne. So ISAT 1 was the first US satellite. They'll be followed by ISAT 2 maybe next year or 17-18 it is proposed. So this was the first airborne laser sensor. And these are some of the geospatial data sources from where you can get different kind of information data sets. Bhuvan is one where all Indian resources, satellite data sets are available. Even thematic layers which have been generated are uploaded on it. Along with that, as I said, the digital elevation model. You can work with it, you can do query, even processing, and probably you'll have an overview onto it. And similarly from the USGS satellites, for the US satellites, Google Earth of course is there, which provides you the data sets of foreign satellites at variable resolutions, generally with high resolution onto it. So with this, I just would like to summarize on the overview part.